This begins our discussion on the support for subroutines within the PIC24 instruction set. When writing code, it is often that you have tasks that need to be done more than once. Here, the sequence of instructions here is executing a task that needs to be done repetitively. So one way to do it is to simply place it in your code every time that you need to do it. A better way to do it that saves program memory space is to only place it in program memory once and then use what's called a subroutine call to execute this code whenever you need it. In this case here, what I'm doing is I'm going to be executing this code starting with instruction 1. When I reach the subroutine call, I'm going to jump here. I'm going to execute this instruction sequence, and then I'm going to return to the instruction following where the subroutine call. I'm then going to pick up execution here. I'm going to call the subroutine again, execute it, and return again to the instruction following the subroutine call. This slide shows a general form of a C subroutine. By the way, different high-level languages call subroutines by different names. In C, the name is function. So a C function has a function name, has a parameter list, and has a return type. Brackets define, enclose the body of the function, and there's an optional return statement you can use that will return the value of the function. Not all functions have to return a value, so you can have functions without this. Here's just an example here. It's a count1's function. It takes one 16-bit parameter. It's going to return an 8-bit data type. This code here is simply going to count the number of 1 bits in this 16-bit variable, and it's going to return it in this local variable U8 count. Here in the main function, we're going to have we're going to call the count1's functions and pass it this value U16K. Its return value is going to be copied into this 8-bit variable J. To support subroutines in the PIC24 instruction set, we need some mechanism for implementing the call and return of a function. So here we're going to try simply using what we already know, which is a goto statement to do this. So here at label C1, we're going to go to a subroutine that we're going to call A. We're going to execute our instruction sequence. Now we need to return. So let's just go ahead and go back to this label immediately following this goto statement and pick up execution here. Now we're going to go ahead and we're going to call this subroutine again. So we'll go to subroutine A here. Now at this point, when we go to return, we have a problem. Instead of returning here at label R2 where we want to return, we're going to return back to the place where we first made the call. So the problem is in supporting this in the PIC24 instruction set, a goto is not sufficient because we need some way to return to the instruction immediately following where we actually called the subroutine. So this means we're going to need some sort of new instructions to implement this call return mechanism. The basic problem in implementing the call return mechanism is remembering where to return to once a subroutine is finished. We're going to talk about a data structure known as a stack, which is a basic data structure that is going to be key in implementing the call return mechanism in the PIC24 instruction set. So let's start with the empty stack. There's nothing on here. Let's view this as a stack of cafeteria trays where we've labeled each tray with a letter. So I'm going to put a tray on top of a stack, and it's going to be called A. I'm going to put another tray on top of that. It's going to be labeled as B, and a third tray on top of that I'm going to label as C. Notice that the last tray I put on the stack is actually the first tray that I would take off the stack. So a stack data structure is also called a last in, first out data structure, a LIFO. So let's begin taking trays off the stack. So when I take the first tray off, that's going to be tray C. Take the next tray off, it's going to be tray B. Take the next tray off, it's going to be tray A. Whenever I place data on top of a stack, I'm saying that I'm pushing data onto the stack. Whenever I take data off the top of a stack, it's said that I'm popping data off the stack. The stack data structure supported the PIC24 via push and pop instructions. The push instruction is how data is copied to a stack. Pop operation is how data is copied from the stack. In order to implement a stack data structure, a pointer known as a stack pointer is used to point to the top of the stack. Here in this example here, the stack pointer is pointing to the first free location of the stack, and in this case we're going to use 900 as that location. When we push this data A onto the stack, that data is going to be copied to that location, 900, and then the stack pointer is going to be incremented to the next free location, which is going to be the word location 902. On the PIC24, the stack pointer is implemented as working register 15. Notice that this push operation is simply a move in which we're taking a source operand and we're copying it to a destination operand that uses the addressing mode register indirect with post increment using working register 15. A pop operation is simply the reverse of a push. When a pop is done, the first thing that's going to be done is that the stack pointer is going to be decremented by 2, in this case from 902 to 900, and then the data is going to be read from that location and written to some destination operand. Notice that this is the same as a move operation whose source addressing mode is going to be register indirect with pre-decrement using working register W15. This value is then going to be written to some destination. The various forms of the push and pops instructions are shown on this slide. This push here, the source operand is specified as either a working register or uses one of the various indirect addressing modes. This form here allows you to push the contents of a memory location onto the stack. This double word push allows you to specify the source operand as one of the 16 source working registers. These forms of the pop, they are the same forms of the push and use the same addressing modes. Let's take a look at some push and pop examples. This is an instruction says push W0 onto the stack. The initial register contents are here. Recall that our stack pointer is W15. It has a value of 950 in this case, so the stack is pointing to this location. When we're going to push, we're going to write the contents of the source operand, which is W0, to the current location of the stack pointer, which is going to be 950. So CD18 becomes a new value of location 950, and then the stack pointer is incremented to the next word, so the stack pointer, which is W15, is going to have a final value of 952. This is the same operation as doing a move W0 to the destination specified by register indirect with post increment using W15 as the pointer register. This is going to illustrate the memory form of the pop, or I'm going to say pop the contents of the stack to memory location 800. So the stack pointer W15 is currently 952. So to do the pop, I first decrement the stack pointer by 2. Then the contents of this memory location, which is CD18, is going to be written to memory location 800. So the final modified values are location 800 has CD18, and W15 has a 950 after 2 has been subtracted from it. Note that this pop instruction is semantically equivalent to a move. Source operand is register indirect pre-decrement using W15 to the memory location 800, but that if you try to do this with the move instruction, it's actually an illegal form of the move. Recall that we began discussing the stack operation when we were trying to figure out how to remember the return address for a subroutine once we called it. Well, the answer is simple. We're going to use a stack to say the return address. Let's talk about some new instructions. We're first going to discuss call and rcall. The R stands for relative call. These can be used to call a subroutine. The call instruction is 2 program words, while the relative call is 1 program word. The call can call a subroutine located anywhere in program memory, while the rcall is limited as to how far away the subroutine can be located away from the rcall instruction. This is similar to the difference between the goto instruction that was 2 words and could jump anywhere in memory, and the branch always instruction that was only 1 word but had a limited branch distance. Each of these instructions, call and rcall, does the same thing. First, they push the return address on the stack. The return address is defined as the address of the instruction after the call and rcall instruction. That's going to be the instruction we want to pick up execution when we return from the subroutine. After it pushes the return address on the stack, then it does an unconditional jump to that subroutine. Once the subroutine has finished executing, you will use the return instruction to return from that subroutine. It's going to pop the top of the stack into the program counter, causing a jump to that location. Under normal conditions, that is, your subroutine has manipulated the stack correctly during its execution, the value that is popped from the stack will be the return address that was pushed by the call rcall instruction that was used to jump to this subroutine. Let's take a look at some numerical examples how call and return manipulate the stack during execution. We want to start by executing this instruction right here, which is call the subroutine A. This is sitting at program memory location 240. The call instruction takes two program words. These two words right here are all part of the call subroutine A. Ignore this no-op mnemonic right here. These two program words implement this call subroutine A instruction. The first thing that call subroutine A is going to do is it's going to push the return address on the stack. Well, what's the return address? The return address is sitting at 4 plus whatever the address of this instruction is. It's sitting at the next instruction following this call, which is going to be 244. The stack pointer was initially pointing at location 900, so it's going to push the program memory address 244 into the stack. Now, when this address is pushed, it's actually pushed as two words. The reason it's doing that is because the program counter, recall the program counter is actually 23 bits wide. So that means we need more than one word of memory to actually store this return address. So it's going to take two words of memory to store the return address. So the stack pointer doing a call is actually going to be incremented here by 4 and is now going to be pointing at 904 after this call. Once that push of the return address 244 into the stack is done, we're then going to jump to subroutine A. Once we reach subroutine A, we begin execution. At this point, recall that our stack pointer is now pointing at 904. Here we're going to do a call to subroutine B. Same as before, we're going to want, first thing that's going to happen is that we're going to push the return address for this call onto the stack. The return address for this call is the address for this instruction, which is going to be 026E. So this is going to be pushed right here as these two words 026E onto the stack, and our stack pointer is going to be incremented to 908. At that point, we're going to do a go to subroutine B. At subroutine B, we're going to keep executing. By the way, these are called nested subroutine calls, in which I'm calling subroutine A, then I'm calling subroutine B, and so forth. Inside subroutine B, I'm going to begin executing this instruction. Then I'm going to do an R call of subroutine C. So again, I need to push the return address for this onto the stack. The return address for an R call, because it's only one program word, is going to be whatever this address of the R call instruction is plus 2. So the return address for this R call instruction is going to be the address of this instruction here, which is going to be 033E. So now the stack pointer is sitting at 908, so I'm going to push the value 033E onto the stack, and when I finally get to subroutine C, my stack pointer is sitting at 90C. So now that we're in subroutine C, we're going to begin executing instructions. This subroutine is not called any other subroutine, so eventually we will hit a return statement. A return statement is going to pop the top of the stack off into the program counter. So that means that my stack pointer is pointing right here. It's first going to decrement it by 4 because my return address takes two words of memory, and then it's going to load this value right here, 033E, into the program counter. That's going to cause a jump to this location, 33E, which is this guy right here. So we're returning here. We're now going to execute that instruction, and now we're going to do another return. So this return is going to now decrement the stack pointer by 4 and then pop this into the program counter. So our program counter is going to get a 026E loaded into it, which is the address of this instruction, which means we're now going to begin executing, and now we're going to hit this return. So at this point, we're going to do another pop return address off the stack, so we're going to decrement the stack pointer by 4, load this value into the program counter 244, which is this, and at that point we're back where we started when we called subroutine A, and so now we're here, and we're going to go to here and get stuck in this infinite loop. So this is an illustration of how the stack is manipulated during call and return. Here are the various forms of the call return instructions. Here we're going to do call to some label. Here we do rcall some label. These will be the forms that we use in all of our examples. There's also a form here that the subroutine address can be contained in a working register. We're not going to use that in our code. This is going to be the form of the return instruction that we use in 99% of our code, in which we simply do a return. You can also do a return literal. This does return, but it also copies an immediate literal value into our working register as part of that return. This is useful for a function that returns a constant value as its return value. Now that we know about call and return, we can now write PIC24 assembly code that implements C functions. Before we do that, however, we want to talk about some rules on how we're going to use registers for subroutine parameter passing and local variables, and also for returning values from functions. These rules are the same rules that are followed by the PIC24 compiler that we use. First of all, registers W0 through W7 are used for parameters, for passing parameters, left to right order. W0 to W7 are also caller saved. The caller is the code that calls the subroutine. And what that means is that the caller wants these registers preserved, and by preserved it means the same values will be in them once the subroutine returns. Then the caller has to save them. How do you save them? You can push them on the stack before you do the subroutine call, and then pop them off the stack after the subroutine call. A function value, if it's returned by the C function, is going to be returned in these 4 registers. If it's either an 8 or 16-bit value, it's returned in W0. If it's a 32-bit value, then we're going to return the least significant word in W0, the most significant word in W1. If it's a 64-bit value, then these 4 16-bit registers are used to return the 64-bit value. Within the subroutine, registers W8 to W14 are said to be callee saved. That is, the subroutine, if the subroutine uses these, then it needs to save them. Again, by pushing them on the stack before using them. For local variables, the subroutine is free to use unused W0 to W7 registers, and it can also use W8 to W14. Note that if it uses unused W0 to W7 registers for local variables, then it doesn't have to save these variables, because the assumption is that if the caller wanted these registers saved, then it would save them. However, if the subroutine uses W8 to W14, then it's going to have to preserve those values. So let's examine implementing a subroutine in PIC24 assembly language. So here's a C function. It takes one parameter, U16V, returns an 8-bit result. This code right here, as we mentioned previously, is going to count the number of 1 bits in the 16-bit value. So let's begin implementing an assembly language, and let's plan our register usage. As per our rules, this parameter right here is going to be passed in W0. The return value, this guy that we're returning here, is going to be returned in W0. We have 2 local variables here, this guy and this guy here. So what we're going to do is we're going to say this local variable here is going to be assigned to W1, and this variable here is going to be assigned to W2. Recall that we do not have to preserve the values of W1 and W2 in the subroutine, because these are going to be caller saved via our rules. So let's get started. We first going to want to clear our count variable, which is W1, so we'll clear that. For this for loop right here, which is actually essentially a while loop, we need to initialize our loop variable I. So we're going to clear that to a 0, so we'll do that. And now we need to do this comparison. So we need to compare our loop variable U16I, which is sitting in W2, against the immediate value 16. We'll make that comparison. In terms of this branch, we need the false branch to escape this loop. So the false branch here is going to be greater than or equal unsigned. So we're going to do a branch on greater than or equal unsigned to the end of our loop. If we did not take that branch, then it means that I is less than 16 and we want to execute the loop body. At this point we want to implement our if body. The first statement in our if body is an if statement. The if statement is testing the least significant bit of this variable v. If that bit is non-zero, then we're going to increment our counter. Let's get started. We first want to do this test. We're going to do that test via this instruction, bittest.z w0, which contains v, number 0. So we're testing the least significant bit of w0. What this instruction does is it copies the complement of that bit into the z flag. That means if this bit is 0, then the z flag will be true. And in the case of the bit being 0, we want to branch and skip the if body. We only want to execute this if body if this test is non-zero. To implement this if body, we need to increment count. Count is being held in W1. So the if body consists of one statement, which is going to increment W1 and place the result back in W1. So this if statement here was implemented by these 4 instructions here. After the if body, we now want to do this shift where we take our variable and shift it to the right by 1. Since this is an unsigned variable, we're going to do a logical shift right of W0, which contains variable v, by 1, stick the result back into W0. At this point, we now are here, which means that we're going to execute this portion of the for loop, which says to increment our loop counter I. Our loop counter I is being held in W2, so we're going to increment W2 by 1 and stick the result in W2. And now we need to jump back up to the top of our loop. When we exit this loop, the last thing that we need to do is we need to do a return and return this value. Recall that this value count is being held in W1, but it needs to be returned. The return value needs to be passed back in W0. So we're first going to copy W1, which has count, into W0, and then we'll do a return. At that point, we have finished implementing the code for the C function. Now that we've written PIC24 code to implement our C function, let's write code that's going to call it. Here in the C code, we're going to initialize the 16-bit variable k to this constant. We're going to pass that to the count1 subroutine, and we're going to assign its return value to this 8-bit variable j. Let's implement this code. Here, we're going to initialize k by taking A501, copying it to W0, and then writing that to k. Now we need to do a subroutine call. First thing we need to do is initialize W0 here, wreg, with the contents of k. Then we're going to call our subroutine by doing rcall count1s, and now we need to take the return value, which is returning in W0, and we need to copy that to j. At that point, we have finished calling our subroutine. Let's talk a little bit about this code here, which is modeled after the type of code that is generated by the PIC24 compiler. Recall that on power up, that the first instruction that's executed by the PIC24 sits at location 0, and what's going to be placed here by the compiler is a goto to this special label called _reset. This code sitting at this label is going to initialize the processor. Well, what type of initialization has to be done? Well, for one thing, the stack has to be initialized. So the special label here, _sp init, is generated by the compiler, and it specifies where the stack begins, and it's a free space in data memory, and that's going to be loaded into W15, which is our stack pointer. The special label here, _sp limit _init, is also going to be written at W0, and then that's going to be copied to a special function register called splim, which stands for stack pointer limit register. What this register does is it marks the end of the stack. If our stack pointer ever exceeds this value, then it said that the stack has overflowed, and that's an error condition, and the processor is going to indicate that error condition. We'll talk about how it does that whenever we start talking about hardware features of the processor. So this code is essentially initializing our stack pointer and our stack pointer limit register, and then we're going to call main. Now main should never return in the code that we write, and we try to illustrate that by making sure that we get caught in an infinite loop down here so we never return. However, if you do return, then this instruction right here, the reset instruction, is called a software reset, and what that does is simply going to cause a jump to the instruction located at instruction 0, and then when that happens, we're going to go back to this reset and start all over again. Recall that our PIC24 implementation of the count once function used the W1 and W2 registers for local variables. We did this because we knew that the rule says that unused registers W0 through W7 that are not used to pass parameters can be used for local variables, and the subroutine does not have to save them. That's the responsibility of the caller. So what if the caller wanted to save these registers? How would you do it? Well, you simply push them on the stack before the call and then pop them off the stack after the call. So here we're going to do a push W1 on the stack. We're going to push W2 on the stack. We're going to move K to WREG to pass a parameter. We'll call the subroutine, then we'll take the return value that's sitting in W0 and we'll move it back to J. At this point, we want to restore these registers, so we're going to do a pop W2 and pop W1. Recall that we need to do this in reverse order because the fact that this is a LIFO structure, last in, first out, so the last thing we pushed in needs to be the first thing that we take out the stack. We could have pushed these in any order. It doesn't matter the order in which we pushed them. You just have to pop them in the reverse order that you pushed. Let's briefly discuss how global variables are initialized. If we have global variables that are scalar values, then what's going to happen is the compiler is going to generate some code in this reset code that's going to initialize their variables so that when we get to main, they have the correct values. For arrays, it's a little bit more complicated, but it's the same idea. Here we have two string arrays. They're sitting in data memory, and they're going to have these initial contents when we enter main. So how is that going to be done? Well, there's going to be a subroutine call generated by a compiler in here that's going to be something like this, in which you're going to call some code called init variables that's going to make sure that these values are initialized. How does the compiler do it in the case of string constants? In the case of string constants, these values are actually going to be stored up in program memory. It is possible to store data in program memory. It doesn't have to just contain instructions. The advantage of storing this data in program memory is that program memory is non-volatile, and it will contain this contents that power up. So thus init variables is going to look in program memory, and it's going to actually copy those values in from program memory in the data memory to initialize the variables. You can look at the code that does that. It talks about it in the book, but we're not going to discuss it any further in this lecture. Let's talk a little bit more about the difference between local variables and global variables. Global variables are assigned fixed memory locations in data memory by the compiler, and we've been using locations such as 800, 802, and so forth in our examples. However, local variables, and that is variables that are declared within subroutines, are assigned by the compiler either to working registers or the space allocated on the stack. It turns out the allocation of stack space for local variables is called stack frames, and that's an advanced topic that we're not going to cover in this class. It is covered in the book and in other slides, so if you're interested about it, you can read about it. It turns out that stack frames can also be used to pass parameters to functions. So given that, in our PIC24 implementations of C functions that we discuss for homework or test problem examples, we will always use working registers for local variables and C functions, and we will always use working registers to pass parameters to C functions. So this wraps up our discussion of topics in Chapter 6. You need to know how the indirect addressing modes work for the PIC24. You need to know how C code operates with pointers and arrays. You need to be able to implement C code of pointers and arrays in PIC24 assembly. You need to understand how the stack on the PIC24 works. You need to know how subroutine call and return works with the PIC24 stack. You need to know how to pass parameters to a subroutine using registers for parameters and locals. And you also know how to implement small C functions in PIC24 assembly.